Thank you everyone for coming to this session of Quantum Spacetime Seminar. Today we have Alex May from the University of British Columbia, and he's going to tell us about quantum tasks require islands on the brain. Over to you, Alex.
Okay, great. Well, thank you. And I just want to start by apologizing for my gaffe yesterday. I didn't account for the date change between Vancouver and India, and consequently missed my time. But an embarrassing gaffe, but hopefully I'll give an excellent talk today and make it all worth your while. So, anyways. Okay, so yes, as was said, I'm talking about a topic I'm calling quantum tasks require islands on the brain. This is not quite the title I sent out via email. This is, I was ambitiously trying to talk about two papers, but decided just to focus on one. So this is based on this archive posting, which is done co-authored with David Wakeham, who I think is around today and might be engaged in questions as well. And yeah, I'll get started. So to start out with something you already know, we know that quantum information now plays a very significant role in the understanding of AdS CFT. And one of the backbones of this connection is, of course, the Ryu-Takayanagi formula. So this says that if I'd like to calculate the von Neumann entropy of some subregion in my CFT, let's call it V, then the way that I can do that is I can look at all the surfaces, call them gamma, that are homologous to V. By homologous, I mean they satisfy this constraint. So there's some codimension 1 surface, call it S, whose boundary is V union gamma. I minimize over all those surfaces, take the area of the minimal one, divide by 4g Newton, and to leading order, that tells me the von Neumann entropy in the CFT. So this is sort of the starting point of this connection, and it has a significance beyond calculating the entropy, in that the actual region that satisfies this, whose boundary is V union the minimal surface, is important. It's called the entanglement wedge, and it's the region of the bulk that's recorded into the density matrix of V. So if I just give you access to V, that's the portion of the bulk that you can learn about. Okay. So this has given us a lot of insight, and one of the recent and exciting places where this has been useful has been in the understanding of black holes and the entropy of the radiation emitted by black holes. So two things to raise there is, one, it let us derive the page curve from semi-classical calculations in the bulk, which is very exciting. And then two, and maybe even more impressively, it told us when and something about how the interior of the black hole is recorded into the escaped Hawking radiation. Okay. So that's probably familiar, but what I want to do today is talk about sort of a second perspective on entanglement in AdS CFT, and connect that to what I was talking about earlier. So the second perspective on entanglement in AdS CFT is captured by the following theorem called the connected wedge theorem. So the way this theorem works, I'll just state the theorem for you and then describe why I think it's interesting. So the way that it works is you should look at, it says pick 4 points on the boundary of your AdS spacetime. So I'm going to pick these points C1, C2, R1, and R2, and then check if those 4 points scatter in the bulk. So by scatter in the bulk, I mean there's somewhere in the bulk, let's call it P, where you can get to from C1 and from C2, and then from there get out to R1 and to R2. Okay, so it says if you can scatter in the bulk in this sense, then on the boundary there's two associated regions, which we'll call V1 and V2, which have a large mutual information. Okay, so to say that a little bit more precisely, I should define these spacetime regions. So I'll define the scattering region, which is just the future light cone of C1, the future light cone of C2, the backward light cone of R1, and the backward light cone of R2. And when I say that the points scatter in the bulk, it just means that this scattering region is not empty. Okay.
Sorry, Alex.
Yeah.
So scatter in the bulk means you say there's a point in the bulk that is that you can reach from the guys in the past and will also connect to the guys in the future. It's just a causal relation, right?
Yeah. Yeah.
Okay. So if points this way can scatter on the boundary, then by definition they can scatter in the bulk because the boundary is the limit of the bulk.
Yeah.
So in particular, you're saying that this is true as long as the 4 points are causally connected on the boundary.
That would be one case in which this occurs.
Yes.
It's sort of the least interesting case. There's also cases where this region in the bulk is not empty, but considering those light cones in the boundary, it would be empty.
Yes. Okay. Thank you.
Yeah. And that's sort of the more interesting case of the theorem.
Okay. Thank you.
Yeah.
Sorry, Alex. Just before you go on, C1, C2, R1, R2 are points on the boundary, just so I understand?
Yes.
Or okay, thank you.
Yeah, that's correct. Yeah, okay. So I said that if the scattering region is not empty, I should also say, please do continue with questions. In Zoom talks, it's especially appreciated. So yeah. Okay, so I said 2 regions on the boundary will have large mutual information when they scatter in the bulk. And specifically, I mean these regions, which I'll call the input regions. Okay. And those are defined by taking the future light cone of one of the C's. So V1, for V1, I would take, say, the future light cone of C1, but now considered in the boundary geometry, which I'll denote with these hats. And then I intersect that with the past light cone of R1 and the past light cone of R2, again, taken in the boundary geometry. Okay, so in the picture, V1 and V2 are these darker gray diamonds here, right? Formed by the future of C like this, and then the past of R's that come down here. Okay, so that's the statement of the theorem. And then if I,
sorry, Alex, just to understand. So if the 4 points were not causally connected on the boundary,
yeah,
then these two, V1 and V2 would be non-intersecting on the boundary.
That's right. So if the boundary version of this region is empty, then V1, V2 are non-intersecting.
Okay, thank you.
Yeah, because this is this, right? If you just think about the intersections. But yeah, so the most interesting case of the theorem is where this is empty and this is not empty. And then V1 and V2 are not overlapping, but the theorem concludes that they have they have large mutual information. Yeah.
But the theorem also applies in the case where they are overlapping?
Well, the way I have it phrased right now, it's confusing to interpret in the case that they're overlapping, because what do I mean by this? Mm-hmm. But I can rephrase it. So if I now use the RT formula, then I can say that, let's think about the RT formula and just assume they're not overlapping for a moment. Then I know that the minimal surfaces sitting like this, so the minimal surface enclosing union of V1 and V2 sitting this way is equivalent to this mutual information being large. And so I could equivalently phrase the theorem as this scattering region being non-empty implies that the entanglement wedge of V1 union V2 is connected. And then this kind of like nicely handles this question of, okay, are they overlapping or non-overlapping in the boundary? Because the trivial case where they overlap on the boundary, you would just trivially find that this is automatically connected.
Okay, okay, I see. Thank you.
Yeah. But,
So
but this, yes.
these 4 points, do they serve as a trick to get at V1 and V2? Because once you get to V1 and V2, the statement is made completely, discounting these 4 points, right? It's just about the statement is about V1 and V2.
Yeah, so you could start with V1 and V2, and then use those to find the appropriate R1 and R2 and C1 and C2, and then check the scattering region. You kind of cut out for a second, but does that address your question, or you maybe?
Yeah, but the way your final statement is, the saying that the mutual information between V1 and V2 is order 1 over G Newton. That statement does not rely on the. This is just a test for whether, having these 4 points causally connected in this way is a test to get to these regions, right? This statement is still in the vacuum, right? The entanglement entropy and so on.
Oh, in the vacuum. So this doesn't have to be in a particular background. This is you can prove this. You just assume the. I'll discuss the motivation for this, but on the gravity side, you can just prove this from the null energy condition. So that's all you have to assume about the bulk geometry and CFT state here.
Okay.
So, sorry, Alex, I got a little lost because I was thinking exactly what you said, but I didn't see how it followed. That is, if I use the entanglement wedge of V1 union V2 as a measure of the mutual information, this is something we would have to prove, right? That if J12 goes to 1, 2, as you define it, is non-zero, not equal to phi, then the entanglement wedge would be of the shape you've drawn, right? That is, would be order 1 over G Newton. Is this automatic? No, right?
No, yeah. So I'm just stating the theorem here, just with no proof and no motivation.
Okay.
So I'm just saying this is a true statement, and we'll get into where this is coming from. Right now, it's coming from just from nowhere.
Okay. But is this something you're going to prove or discuss in the talk, or something that's been shown? Okay. All right.
Yeah.
Thank you.
Yeah, that's right.
Sorry. Is the converse also true? That if V1, V2 have this
the converse is false.
Is false. So you need not be you necessarily. It's not necessary that you will find such 4 points, right? If you have, that's what I mean. Okay.
Yeah. So it does not follow that it goes the other way. Okay. It's both ways in the vacuum or the pure AdS. With matter, you can find counterexamples. Okay. Yes. So for now, I'm just stating this theorem. I'm gonna motivate a very similar statement. Not quite this one, but I think you'll get a sense of why this one's true. But the reason I wanted to tell you this is just that, one thing I think is interesting here is that here we're seeing some kind of connection between bulk geometry and boundary entanglement, which is similar to the RT formula. But now, instead of studying minimal surfaces, so somehow spacelike geometry, we're looking at intersections of light cones. And that's qualitatively a bit different than the RT formula. It's a qualitatively different connection between entanglement in the CFT and geometry in AdS. Okay. So what I want to do in the talk today is apply this causal perspective on entanglement to this story of black holes and islands, and see what we learn in that context. So the RT formula was very helpful there, and we learned a lot. Here's a different perspective on entanglement. Can we learn something new? Okay, so the sort of roadmap for getting there will be, first of all, I'm going to talk about the AdS BCFT correspondence, which is just a holographic dual description of conformal field theories that live on a manifold with a boundary. And I'm not sure how familiar that is to people, but you don't need to be, I'll say a few words about it. And that's going to be the context in which we're going to construct some black hole solutions that we're then going to apply this kind of connected wedge theorem to, and see what we learn. Yeah, okay. And then this connected wedge theorem I described on the last slide, that was applied to AdS space. So I'm going to just state some kind of adapted version of this that will apply in the context of AdS BCFT. Okay, then I'll take that theorem and I'll apply it to these black hole solutions and see what we learn. And then finally, I'll come back and motivate this connected wedge theorem and give you a quantum information argument as to why it's true. And time permitting, I can also talk about the relativistic proof of the same theorem. Okay. So I'll jump in unless there's further questions about the intro there. Okay, good. All right, so I'm going to talk about AdS BCFT, and I'll start with the bulk picture. So there, the bulk is described by an action like this. So we have the usual, sorry. My tablet's doing something strange.
Mm-hmm. Mm.
Sorry, one moment. Okay, there we go. Okay, so starting with the bulk picture, we have an action, we have the usual Einstein-Hilbert term, the cosmological constant, some matter that lives in the bulk. So that's describing some AdS space here, or asymptotically AdS space. We have the usual AdS boundary, okay, out here. And then additionally, the spacetime in the bulk just ends on some kind of dynamical object, which is this end of the world brane. Okay. And the brane is described by its own action, and where this is the extrinsic curvature, and there could be some matter fields that are localized to the brane. Okay. And then this would give you some equations of motions that look like this. So you have the usual Einstein's equations, and then an additional equation that's like a boundary condition for the brane. It governs the brane. Okay. Yeah, just to introduce some useful language. The brane will extend out to the AdS boundary somewhere, and where it meets the AdS boundary, I'm going to call the edge. Okay. Otherwise, there's too many things called the boundary. Okay, so that's the bulk. Some dual description for this, or at least proposed dual description. So I've drawn a time slice here. I have my AdS space, my AdS boundary, my end of the world brane, and my edge. And then in the boundary, that's described by a CFT that lives on the AdS boundary. And then at the edge, I have some boundary conditions set on my CFT. And then that, that boundary for the CFT extends into the bulk in some way as this end of the world brane. Okay. So the theorem I'm going to give you applies generally to this kind of model, but the specific black hole solutions I'm going to study take a bit of a special case. So there, we're going to
sorry, Alex, can you tell us where this comes? This is just some rules somebody's announced, or why do we have a brane with some tension? Why does spacetime end in this way? Is this supposed to be some rough phenomenological description of true solutions of string theory? Or, what is the status?
Yeah. So, to be honest, I'm not an expert in exactly motivating this, but this was proposed by Taganaki actually quite a long time ago, and he was just motivating it by basically you can study entropies in BCFTs in this conformal field theory on a manifold with a boundary. And he was just observing that this model with the okay, so the simple case I was going to describe, you choose a matter Lagrangian on the brane that just looks like this, where T is a constant. And he was observing that various features of BCFT are reproduced by a constant tension brane, including, for instance, the von Neumann entropy of subregions. There's been a lot of work since then on more microscopic top-down models where we have some specific CFT with a boundary condition set. And there's a more detailed description of, how this space-time ends. Usually some field will blow up, or I guess there's cases where it sort of smoothly caps off. So some sphere's radius shrinks to 0. And people who study these microscopic models tell me this is a reasonable description of, a reasonable bottom-up description of those.
So it's a rough phenomenological description of many true models. Is that right?
Yes.
Okay, so we should only trust rough qualitative things that come out of it, not precise statements.
I think that's fair, yeah.
Okay, thanks.
So, Alex, given that you are describing the action on the brane, in detail, doesn't it mean that the boundary condition that you use also needs to be very specific so that it is dual to your description of the bulk, this end of the world brane? Because here you didn't quite specify the boundary condition very precisely, right?
No, I haven't described the boundary condition very precisely. I guess basically, I think the way to think about this is that, in microscopic models, there's many different, very detailed ways you could set the boundary condition. But at this kind of phenomenological level, we can just think of one parameter that describes sort of the number of degrees of freedom that live at the boundary. Mm-hmm. And so, in the CFT picture, I'm just going to have some number describing the boundary condition. And then that number is going to be related to this number, which is the tension that describes the end of the world brane. I don't know, is David here? He might have something to weigh in. He studies these things. Oh no, I guess he wasn't able to make it, but.
Oh no, I'm here.
Oh, you're here, yeah. I don't know, David, would you say these are fair comments about AdS BCFT?
Yeah, and I think there's some parameter regime where we expect them to be sort of a good description in some sense, sort of like taking the large C limit. There are various statements you can make about correlators and so forth, where you will have corrections to these rough qualitative things, but the corrections are subleading. So here we expect that there should be some similar set of limits one can take for various parameters where the corrections are going to be subleading, and the statements we make will be good up to those corrections.
And can you say again, what is the parameter regime where the boundary central charge goes to infinity?
Yeah, so I think typically you'll take these tensions to be proportional to G, proportional to C. So we'll take, usually a bulk description so that there'll be some semi-classical limit where G goes to 0, and there'll be some kind of additional microscopic constraints on the boundary condition. So usually you'll have to say something like small sources for fields which live on the boundary, so that the bulk description remains good. So that will generally constitute some sort of additional set of microscopic constraints and kind of some sort of additional set of semi-classical like constraints, which are kind of over and above the usual ones for AdS CFT.
Yeah.
So just one more question. Is the primary set of examples these D3, D5 kind of the Guyotto-Witten kind of geometries? Is that a set of examples one could study in detail? And
I think Chris is currently studying those in detail.
Yeah, definitely. So these are the nicest kind of microscopic examples that have been worked out. You can also study these from kind of the sort of CFT side, but from a string theory perspective, then yeah, these D3, D5 systems are the nicest ones, I think.
Yeah.
Thank you.
Okay. Yeah. Yeah. Okay. So within the sort of model we're working in, we just have this one number describing the edge in the CFT, this one number, the tension describing the brane. The bulk and boundary parameters are related in the way I've written here. So we have the usual relationship between the CFT central charge and the bulk AdS length, and then this relationship between the edge degrees of freedom, the edge central charge, and the tension. Okay. So we don't need to know a ton about this, but the thing I want to say is just that Ryu-Takayanagi still makes sense or still holds. You just need to be a little bit careful about the homology constraint. So we still have this statement. It's just that now when we minimize over surfaces, we want to minimize over surfaces satisfying this constraint. So the region V union the surface I'm looking at union any portion of the end of the world brane should be the boundary of some codimension 1 surface. Okay. So what that means is if I have some region here V, then there's 2 surfaces homologous, or 2 candidate surfaces homologous to V, which is the ones that sit like this, and then the ones that sit like this and attach to the brane.
Sorry, V is the boundary?
V is some subregion in the CFT.
Yes, okay, thank you. And so the top line here is your end of the world, right?
Yeah. Good. Okay. Okay. Good. Okay. So the particular solutions we're gonna study are the following things. So we're gonna take this simple choice for the bulk matter Lagrangian that I mentioned, where we just have a constant tension brane. We're gonna work in D equals 2. And then we have the following solutions. So we will just write AdS 2 plus 1 in a particular way. So this is just pure AdS 2 plus 1, but it's written in these slicing coordinates where I have a lower dimensional AdS, and then those are warped together with this coordinate row. And it's convenient to write AdS 2 plus 1 in that way because I can solve these 2 equations of motions that I mentioned before by just having a brane sitting at a constant value of rho. Okay, and that constant value is related to the tension by this arctang. Okay. Okay, so that's AdS BCFT. Those are the solutions we're going to study. Now let me give you the version of this theorem I mentioned earlier that will apply in the context of these branes, these end of the world branes. Okay, so here it is. I pick now 3 points on the boundary. So I have C1, which will be in the AdS boundary. And I have R1 and R2, which I'm going to choose to sit in the edge. Okay. And then there's a scattering condition again. And now the scattering condition is that there's somewhere on the brane, which is in the future of C1 and the past of R1 and R2. Okay, so that is recorded by saying that this region is not empty, where that region is the future of C1, the past of R1, the past of R2, and then restricted to the brane. Okay, and then the statement of the theorem is that if that happens, then the entanglement wedge of V will be attached to the brane. So its intersection with the brane will be non-empty. Yes, okay. And then, yeah, so the region V is defined just like before. So it's the future of C1, the past of R1, the past of R2 in the boundary geometry. Any questions about the statement of that? That's okay. It's very similar to before. Yeah, and then I'm going to talk about the quantum information motivation for this later. But I'll just say that the relativistic proof of this assumes two things now. So it assumes the null energy condition on the stress tensor in the bulk of AdS. And then it assumes the null energy condition applied to the intrinsic stress tensor on the brane. So from that matter Lagrangian on the brane, I could define the stress tensor, and LA and LB are null vectors that are tangent to the brane.
So, sorry, Alex, just want to make sure. What's capital B in J1 goes to 1, 2? It's the whole brane. What's capital B, please?
Oh, sorry. B is the whole brane.
Whole brane, I see.
Yeah.
Okay. Well, that means the entire world volume, I suppose, huh, of the brane.
Yes.
Yeah. Okay.
With its extent time. Yeah.
Extent. Yeah. Okay. Thank you. Got you. Okay.
Good. Okay. Okay. So that's the theorem. I'm not actually going to apply the theorem. I'm going to apply its time reversed variant. Okay. So I'll just take, so I can reverse time in general relativity and get true statements. So I just flip all the pluses to minuses in the statement I had before. Now I have a C at a late time, and R1 and R2 at some early time. Otherwise, it's the same thing. Okay. Okay. So now I'm going to try and apply this in the context of islands. And so I want to come back to this black hole, this solution I was talking about before, and discuss why it looks like a black hole in some sense. Okay, so I had these global solutions described by this kind of metric here. This was the 1 + 1 d rho squared. And what I'm going to do is take a Poincare patch of those global solutions. And so the patch is shown partly dashed here, right? And then it comes around like this, and up like this. And so it picks out this chunk of the global solution that's bounded by the end of the world brane on one side, and then these two sort of wings of the CFT here. Okay. If I'm just looking inside the patch, the brane looks like a black hole in the sense that there's a horizon separating the left and right edges, right? So this edge, or the extent of this edge that's in the patch, will be pi, and then the light travel time across the brane will also be pi. So if I start a signal here somewhere, it will leave the patch before it reaches the other edge. So there's some horizon like this and like this that separates my two edges. Okay, so this is just sort of a usual statement that global AdS 1 + 1 looks like a black hole, because that's the brane is just global AdS 1 + 1. Okay. Okay, good. And then I'm going to focus on the large tension case. And there's sort of two reasons to do that. So I guess I didn't spell this out before, but one thing to say is that the large tension or positive tension is where the brane comes out, and I get like extra AdS space in the bulk here.
Sorry, Alex.
Yeah.
One clarification. So far, all the things that you said didn't quite depend on the dimension, right? They were valid now. Any dimension, but now you specialize to b equals to 2 for CFT.
Yeah, I'm thinking about these solutions that are in 2+1 dimensional AdS.
Okay, but the connected wedge theorem, etc., they were valid in general dimension. Is that true?
Yeah. So that the connected wedge theorem will be true in general dimensions, but there is a question of when are you in a non-trivial case. So yeah, I haven't thought about this as hard for the brane version of the theorem, but if we think about just the AdS version of the theorem, then in 2+1, it's very easy to come up with cases where you scatter in the bulk but not the boundary, and this is the non-trivial case of the theorem. In higher dimensions where your boundary is a sphere, it's actually, if I just choose points like this, it's actually not possible to do that. You'll always scatter on the boundary. But yeah, I've been in separate work, I've been working towards a version of this that keeps applying in arbitrary dimensions, but that's kind of ongoing. So
thank you.
Yeah. On the other hand, if you go to higher dimensions, but you make your boundary a cylinder, so you're in the AdS soliton, then it's non-trivial again. So I don't think the physics of it is really unique to low dimensions, but somehow I just don't know how to say it the right way in higher dimensions. Yeah.
Alex, sorry, since we paused, I just want to make sure, when you stated your theorem for the brane, end of the world brane case, which is, I think, 2 slides back, there was something called V here in EWV union B, or V defined. Okay, that's what I was looking for. Sorry. Okay, it's just the intersection of the J hats. Thank you. Go ahead.
Good. Yes. So it's the input region. Now there's only one input region because there's only one.
Yeah. Got it. Okay. Thank you.
Okay. Yeah. So we have black hole. Okay. Yeah. So we're gonna think about the large tension case. That's the case where the brane extends far out like this. One of the reasons it's nice to take this case is that it's in that case where the edge describe the black hole or describe the brane. And one way to see that is just to take a little interval near the edge and look at its entanglement wedge. And you see that this thing's area will keep growing and growing as I push my brane out. And at some point this becomes favorable. And so the whole brane is in the entanglement wedge of just these little intervals near the edges. Okay.
One question, Alex. Sorry. Yeah. When you look at this edge, is the boundary condition conformal on the edge?
Yeah, so you try and preserve as much of the conformal symmetry as you can.
Okay.
Set the
so if you take the edge to be, let's say, some flat codimension 1 boundary for the CFT with conformal boundary conditions, then from symmetry, wouldn't your end of the world brane have a very specific profile so that it should preserve the maximum symmetry that is preserved by this flat boundary condition, flat conformal boundary condition?
Yeah, and I suppose that must be the profile picked out by this, like the profile is fixed by this equation in the bulk that in the coordinates I've chosen is rho equals rho naught.
Mm-hmm. Mm-hmm. Okay.
Yeah.
The geometry of the brane is just hyperbolic, right? Like the metric on the metric on the brane is just hyperbolic, right?
Yeah, it's just AdS 1+1.
Right. Okay. Thank you.
Yeah. It's a lower dimensional AdS.
Sorry, Alex, you're saying in your slide you have focus on the large t approximately equal to 1 case. Why isn't, firstly, what is 1? This is 1 in units of AdS radius, and why is it 1 large?
Well, I wrote down that expression before where t was tanh of C edge over C. Yeah, I guess I could be missing some. Oops.
This must be in G Newton units. No, I was thinking when you wrote.
Yeah, sorry. I guess I've set some things equal to 1 here. I'd have to think to restore the units, but yeah, basically there's some finite range of tensions which makes your brane sweep out, like being here to being here to extending flat out here. And so, yeah, I just mean a tension such that you're close to you're coming off the edge almost flat.
So there's a maximum tension that your end of the world brane is allowed to have?
That's right, yeah.
And you're reaching that maximum, okay. And you say you reach that maximum when the central charge of the boundary goes to infinity. Is this
That's
right?
right. So this is C edge, much bigger than C.
What would your diagram look like in the opposite case where C edge went to 0? Would it be?
It would look like this. So you'd cut out most of your AdS space and just have a little slice.
Okay. So I'm going to ask a question that is not very precise, but
yeah.
One limit of this, one fascinating statement you're making is that in the limit that the C edge goes to infinity, the fact that you've lost part of your boundary seems almost not to matter as far as the bulk is concerned, because most of the AdS is in the bulk anyway.
That's right. Yeah.
Okay. And somehow, because you've got so many boundary degrees of freedom, that's making up for not having boundary of the boundary degrees of freedom. That's making up for not having part of your boundary. Okay. Yes. But the other limit seems less intuitive to me. That is the other limit where you've got almost no boundary degrees of freedom. You're saying you're losing almost all of the bulk.
Yeah. So
yeah, why
it's a little bit contested. So in the sort of bottom-up model we're working in, there's no reason to not have a negative tension. Right. So these are negative tension, t less than 0.
So just to be clear, that would be C edge goes to minus C or something like that, right? Or C edge gets large and negative.
Yeah, that's right. So some people don't like negative tension end of the world branes and think they, from a microscopic perspective, don't make sense.
I see. It's like having negative degrees. It's like your boundary of the boundary is eating up some of the degrees in the bulk of the boundary. Okay, fine. But t equals 0 would be just the brane going straight down.
That's right. Yeah.
Okay, so that's like cutting AdS into half, right? If you took half of the boundary, you have half of AdS. So,
yeah.
Okay, fine. Now that makes sense. Thank you.
Yeah. Okay. Yeah, it is very interesting actually that you seem to restore a whole AdS space just by adding degrees of freedom at the edge, and I think Mark has been very fascinated by this idea, and that's played into some of his recent work. Right. Okay. So at large tension, the edge describes the brane, and then another interesting thing about large tension is that from this classic work of Randall and Sundram, large tension branes in AdS space have a lower dimensional effective gravity that localizes to them. And so you could also you can sort of think about a effective theory of gravity that just lives on this brane, at least in this limit. Okay. Okay. So what I said on the last slide is that from the CFT perspective, we should think of the edge as the black hole, right? Because the edge describes the brane, which is our black hole. And then what we're going to do is think about the rest of the CFT as the radiation system. And the edge is going to interact with the rest of the CFT, and information is going to leak out of the edge and into the CFT, and that's going to be information escaping my black hole.
So by black hole, you mean just Also, the black hole is what? What, please? It's part of includes the end of the world brane plus some region of space-time.
Yeah, I guess it does. I mean, that's a little bit awkward. I really want to think of the black hole as being just this portion of the brane that sits in the patch, but yeah, I suppose you're right that actually the edge also includes this region in here. Yeah, that's maybe a bit of a defect in the kind of model we're building.
Thank you.
Yeah. Yeah. Okay. So because large tension is like this edge. This number of edge degrees of freedom being much larger than the CFT degrees of freedom, you should also maybe think of this as setting some like slow time scale over which information gets out. Okay. Good. Okay, so then what we're going to ask is what portions of the CFT, i.e. the radiation system, reconstructs the black hole interior? You know, how much Hawking radiation do I have? It's the analog of saying, how much Hawking radiation do I have to collect before I start seeing into the black hole? Okay. So there's two ways to do this. One is to use minimal surfaces. The other is to use this connected wedge theorem that I was describing. The minimal surface way was done already. And it's these authors' model that I'm following here. So this is a paper by many people at UBC, so including David, who's here, and on this paper, and then Moshe Rizali, Jamie Sully, Mark Van Ramsonk, and Chris Waddell. And yeah, they looked at exactly the setup. So they have their brane here, which is their black hole, and then they look at portions of the CFT, right? And then by studying the minimal surfaces, look at whether those reconstruct a portion of the black hole or black hole interior or not. And that just comes down to checking if this surface is minimal or this brane connected surface is minimal. Okay. And you know what you'll find is what you'd expect. So as you grow your radiation system and look at more and more of the Hawking radiation, at some point there's this transition where you start seeing the interior, and we say that an island forms. So this portion of the entanglement wedge that's attached to the brane is an island in this model. Okay.
You know, I'm sorry, Alex. I'm having. I understand your top right-hand side picture because it's a standard island formula type of picture where you've grown an island.
Yeah. And
the bottom picture is and the branes there are those two horizontal lines, presumably. No, are the verticals? Where are the branes there? Sorry, the end of the world brane there.
So in this picture, this whole square is the end of the world brane. So I've let me go back.
Okay, I see.
So I've taken this and I've drawn everything but the bulk. Okay. So I've drawn the brane with its like wings flattened out. And that's these pictures. So these are the two horizons, right? This is the CFT. And then I've drawn a slice of the higher dimensional AdS space. And this is the subregion V. And then, yeah, this orange portion is this orange portion.
Let me try to process that. Yeah, you go on. I see. Okay. I understand.
Okay. Yes. Okay. So they studied this. That's nice.
Sorry, wait. Just to understand this island region, its ends end on the end of the world brane, but it goes out into the AdS bulk, right?
Yeah.
So this line that you've drawn, if I understood you right, you said this white sort of square that you've drawn is the end of the world brane.
Yeah.
So the points mark the end of the island region, but the orange line that you've drawn there is not really there. That was in the bulk, right?
Well, the orange line I've drawn is the intersection of the entanglement wedge in the higher dimensional space with the end of the world brane.
Okay, but it's not the boundary of the island.
It is not the boundary of the island.
Yes. Okay. Thank you.
Yeah. From the lower dimensional perspective, the boundary of the island is the dots.
Yeah. Thank you.
Okay. Good. Yeah. So this would be the usual way of studying where an island forms, right? You use the RT formula. You look where the transition happens. Okay.
Alex?
Yeah.
Sorry, a basic question. So in this picture here, so this black hole, this radiation process is happening here, right, on this end of the world brane slice that you have drawn here, right? I mean this the region in the black in your
Yes.
In your diagrams. Now that is, as Shiraz is saying, is part of a bigger radius, right? It's just the boundary of a bigger radius.
Yes.
So the energy directly leaks out into that radius from here. So is there a way to study this kind of a process where the process happens by itself and not quite leak, it doesn't leak out into a higher dimensional system?
Yeah, I mean, I guess yeah, there's sort of two ways that people have been, well, there's the two original Islands papers, one where they use this kind of doubly holographic perspective, and there's this higher dimensional AdS space, which is very similar to what I'm doing here. They would have, I mean, the words are a little bit different, but these are very similar pictures. But you can also, in the other paper that came out originally by Jeff Pennington, he was studying just a four-dimensional black hole that was evaporating. There was no doubly holographic picture or higher dimensional AdS. And by using the quantum extremal surface, the sort of full version of the RT formula that includes the quantum corrections,
okay,
you could study where islands form in a more direct way, which I think is the sort of picture that you're asking for.
I see. And these are qualitatively different things. In particular, this is here. It's not an isolated system, this black hole, but there it is. Is that?
Well, here, I mean, I guess one thing is that I mentioned that at large tension, there's like the gravity on the brane sort of decouples from the higher dimensional space, right? There's just like this lower dimensional gravity description. So I think in that limit, you can think about, like there's just gravity on this lower dimensional thing, and you shouldn't really think about the radiation escaping like through the bulk.
Right, I agree. In that case, I would be able to do that. But this gravity decoupling thing. So does this mean that there is a conserved stress tensor also on the edge of the CFT? Because usually that is not the case, right? When you have a BCFT, on the boundary there does not exist a conserved stress tensor, because essentially the energy can exchange with the.
Yeah, that's an interesting question. So you're saying if I have a dynamical metric on my brane, then there should be a way of defining the stress tensor at the edge.
Right,
sort of
right. If you're saying gravity is decoupled and has a, just restricted to the end of the world brane, then I would think that there is a conserved stress tensor. I mean, dual description would be in terms of the conserved stress tensor on the edge.
Yeah, I mean, that sounds plausible. I guess I don't know if I have any intelligent comments about it.
I just don't see why this operator would get developed in the limit that you are interested in. So this limit, if you can, so this limit is the limit of large tension. Is that the limit in which you would have a decoupled gravity on the end of the world brane? That's what you're saying, right?
Yeah, that's right. That's right.
Okay. Thank you.
Yeah. Yeah, I think I don't fully understand the issues well, I understand what you're asking, but I don't think I have perfect answers to what you're asking. But yeah. Oh, okay. So this is the sort of traditional, quote unquote, it's only a couple of years, but perspective on islands and how you see when they form. And okay, but as advertised, what we want to do now is instead apply the connected wedge theorem, which will give us some alternative way to see when an island should form. Okay, so the way to do this is we're going to pick our 3 points, right? And we're going to pick R1 and R2 to be at the beginning of these horizons. Okay, so in the patch, they're at
Sorry, Alex, just to make completely sure.
Yeah.
So in the previous picture, you've taken your original CFT, which had a AdS with the end of the world brane as its dual, and coupled it to additional matter which lives in asymptotically flat space, right? I gather from the 2 scry pluses and minuses.
So this is, it looks like that. Pictorially, it looks like that, but it's not quite so.
I see.
This is just the CFT.
So why is the?
Or sorry, it is in flat space because it's this picture, right? So this is the CFT that originally lived on my AdS boundary. And so these, the CFT, the AdS boundary here is indeed flat space. So those wedges are a holographic CFT that lives in a chunk of Minkowski space.
I see. The boundary here is not the boundary of the AdS, just with the end of the world brane coming and cutting it off partly.
Yeah, that's right.
It's not that. I mean, why is asymptotic infinity like that of a flat space? I'm really confused. Sorry. Why is it? Is that right? I mean, is that what happens with the end of the world brane?
So I'm taking a Poincare patch here, and so the the boundary of Poincare AdS is just Minkowski space.
I see.
And so these
I see. Okay. I see.
Portions of the CFT are indeed living in Minkowski space.
Oh, I see. Okay, that's what's going on. Okay, thank you. Okay, go ahead.
Okay, good. Where was I? Okay, yeah. So we're going to try and apply the connected wedge theorem to learn about islands in this setup. And to do that, we need to choose these 3 points, right? And the prescription for choosing the points is going to be put R1 at the past of one of the horizons and R2 at the other one. Okay. And then C1 is sort of, we're free to place in different places. And okay, we'll put it up here somewhere. And then that will define for us some subregion of the radiation that we're going to look at. Okay. Okay. So that's how we pick our points. And then what the theorem tells us is when those points scatter, right, off the brane, then this radiation system has an entanglement wedge that connects to the brane. And so translating that into this description of the black hole, it says that when the black hole interior is causally connected to the radiation system through the auxiliary geometry, then that radiation system forms an island. Okay. And it's slightly awkward here in that my radiation system sits outside of the Poincare patch, or looks like it does. But this diamond here that defines R, I can think of that, the state that describes that diamond is living on any slice here, right? So I can just move that slice back in time, and so it sits right on the at infinity of these portions of flat space. Okay.
Just one question, the causal structure here that's relevant is of this three-dimensional AdS space, which is somehow like the doubly holographic
That's
AdS.
right. Yeah.
Right? Okay.
Yeah. So
There's no statement like that. Oh, sorry, go on.
Yeah, I was just reading what you're saying. So you're looking at light cones in the auxiliary space.
I see.
Yeah.
Why was it 3? Wait, let me get, your bulk is how many dimensions? Is it 4?
It's 2 plus 1.
2 plus 1. And then that's what I thought. And then your light cones are still, are not on the boundary in the Poincaré patch of AdS2. Is that not right? That's what I thought you were saying, that you look at just the Poincaré patch of the boundary of AdS3, and then it's a limit on the boundary. Is that not right?
Yeah. So I guess there's different pictures here. So in, previously when I wanted to think about, yeah. So I guess to apply this theorem, I'm looking at the global spacetime. Whereas in the previous discussion, I was looking just inside of a patch.
Okay.
And then I'm saying, if I look at light cones in the global spacetime,
Okay.
then I get this condition.
Okay, so you say, but because just so I understand, because the end of the world comes and intersects the boundary, it cuts off part of the full boundary of global AdS, I guess.
Yes, that's true.
And the space-time which describes the boundary, then if I kept all of it, would have what kind of a Penrose diagram, just to understand? Would it be
like an interval cross time? So I'm just unrolling this thing here.
So this is that. Okay, I see. And just once, then you must go on. When you earlier drew the asymptotics as chi plus and minus, what exactly were you cutting off parts of this, or just?
Then I was taking this patch here.
Okay.
And then I got these two wedges I've drawn in blue here.
I see. Okay. I see. Okay. Thank you.
Okay, good.
Just a quick question, Alex. So in this case, the connected wedge theorem requires sort of, as I was saying before, requires this doubly holographic or this three-dimensional AdS space. Is there something like you can abstract away from here where you can just like formulate a connected wedge theorem without the presence of a doubly holographic setup? Or
yeah, it's a great question. I'd really like to think about it, but I don't know. Yeah,
sounds good. Okay, thank you.
Yeah, I think that would be the aspiration. Like if there was some, like in say Jeff's picture of just like a 4-dimensional black hole, radiation's coming out, is there some sense in which the radiation system is causally connected to the interior? I mean, yeah, that'd be very interesting to understand.
Okay, thank you.
But yeah, I mean, I think it's, maybe suggested by this, but you could also think maybe this is just an artifact of the doubly holographic picture, and I'm open to that idea as well. That would make this less interesting, but it's possible. Okay. Any other questions? This is one of the main punchlines, so might as well dwell on it.
So should we have intuitively expected? What is there are two things that you've talked about. A, that the causal relationship between this end of the world brane and the radiation system, and B, the entanglement wedge reaching the end of the world. And should I have expected this from general principles of causality, or is it a surprise? Or
I don't know. I mean, I didn't know any obvious argument that this would be true. maybe a better relativist or something would have, but
sorry, I wasn't talking about the technical argument. I meant should we on physical grounds have, I was wondering whether you were saying that it couldn't have been that the entanglement wedge extends up to the boundary unless this was true, because otherwise you would be able to logically violate causality, something like that. Is that true, or it's just, yeah?
All I can say is I don't know of any such argument.
I see. So it's just something that comes out of a calculation, and there was no a priori reason to expect it, as far as you know.
Yeah, I mean, I think, well, okay, so the next thing I'm going to do is tell you where this theorem came from and the sort of reasoning that got us there. That may partly answer your question.
Okay.
I think it gives a pretty good intuition for why this theorem should be true. And yeah, I think so. Maybe we can revisit that question as well when we discuss this. But
okay, good.
Okay. So yeah, one thing to point out here is this theorem gives some perspective on how we can probe the black hole interior using the radiation system. So the idea here is,
Alex,
yeah,
Alex. So this end of the world brane here, you take it to be flat in this AdS 3 geometry, but depending on the tension, it could go and touch the back boundary of this AdS, right?
Yeah, sorry. So I keep drawing the t=0 case.
Oh, okay.
But really, that's the pictures are easier.
Okay.
I'm really more interested in the case where it comes out like this, as you say.
I see. So this criteria that you have developed, it does depend on T. So
that's right. Yeah. So
depending on what, yeah.
This would be further for larger T. This light travel time would be longer, and you'd have to go to a later. Right. You'd have to move C upwards in order to hit the light cone, and then also you need a larger region to reach the minimal surfaces to want to reach out to the brane, and the theorem tells you that those work out.
Okay.
Sorry, Alex. I suppose this is probably very ill-formed, but what I was asking was this: for the space-time degrees of freedom in the brane and inside the black hole to be encoded for outside the boundary, you need something to develop, some strong entanglement or something like that. And is your result suggesting that this happens causally, that this happens from stuff here going out to the boundary and therefore developing? I don't know what exactly I'm asking, but yeah.
Yeah, I think, okay, so this is a little bit in tension with one other thing I think is true, but what this theorem seems to be suggesting is it seems to be saying, okay, how did information get out of the black hole? It just traveled, through the auxiliary space, just on a light ray, causally, and got into the radiation system. That's the picture it suggests, right? And I don't know how seriously to take that, but it's certainly a sort of provocative direction it leads you in.
And that it was needed for this to happen for the radiation system to be able to become the true encoding of that bulk. But until this happened, that couldn't have happened. This encoding of.
Sorry, I thought the converse is not true.
So yeah, okay, that's a good point. I was just going to raise that. So in these models where I have pure AdS and then a constant tension brane, the converse actually does hold. So it is if and only if. So that also supports this kind of picture that Shiraz is suggesting. But if I guess then you have to think about like, well, how artificial was it to think about a constant tension brane? Because if I put a more non-trivial stress tensor on the brane, then the theorem's not both ways. Or if I put some matter in the bulk here, it's also not both ways. So.
Sorry, I'm really quite lost. What's the auxiliary space you mentioned?
Sorry, the auxiliary space, I just mean the higher dimensional AdS
You
here.
just mean the higher dimension.
Yeah.
No, but causally, can stuff from inside the black hole get to the boundary?
In the global space-time, yes. So, yeah. So say this is some point inside the black hole. In the Poincare patch, that's behind a horizon from the boundary, which is like this.
Okay.
But in the global space-time.
Global it can, okay. And just so I understand, we're now taking the global case, is it? If I understand, for your connected wedge theorem?
For the connected wedge theorem, you want to think in the global case. Yeah, you're studying light cones in the,
okay.
In the
global. And just sorry to be so slow. And the statement is you had these 3 points, R1, R2, and C1 or something, right?
Yeah.
And the statement is that, what's the statement vis-a-vis the entanglement wedge here?
So the statement is when you can meet up between R1 and R2 and then get out to C1, where your meetup point should be on the brane.
Yes.
Then this region here in black has an entanglement wedge that connects to the brane.
Connects to the brane.
And in the black hole context, well, the way I want to say entanglement wedge connects to the brane is the radiation system forms an island.
I see. But then just to, perhaps I'm so sorry to be so slow, just to understand it, maybe this is what Shiraz was saying. Shiraz, is it possible causally, because this is a kind of time independent situation in a sense, right? Is it possible that stuff from the island, from your black hole actually reached the global boundary, and from the global boundary reached the shaded region of interest? And that is why, you have this entanglement, so to say?
Yeah, so that's what the geometry lets happen, right? So the geometry says, like, the theorem says that when you can travel from here, which is inside the interior of the black hole, through the global space-time.
There, I see. Okay, that's what you guys were saying. Sorry. Yes, yes, okay.
And then reach C. Then, C is inside of R. And so it's saying the radiation system is, part of it is in the causal future of the black hole interior.
So Alex, from this causal kind of a point of view, isn't it puzzling that you require the meetup point to be on the brane? Because if it is just this interpretation that you're suggesting, that there's some causal propagation, it could have happened through the entire propagation could have happened through the bulk also, through the AdS3 bulk also. But here you are putting this additional, is it natural from this point of view?
I think so. I mean, I think you're just saying, like, I think it's just saying, I want to think about when the black hole interior can reach the radiation system. And so that restriction, of the scattering region to be on the brane is ensuring that I'm actually, that I'm actually in the black hole and not out here somewhere. Right?
You're trying to check whether some point on the brane can be encoded by the radiation. So that's why.
Yeah.
Sorry, sir, does this, there are these pictures that I've never understood, but people keep drawing these ER is equal to EPR sort of wormholes. And so are you saying somehow that in the lower dimensional, the two-dimensional, what would have been ER equals EPR wormholes in the two-dimensional picture become just ordinary causal propagation in the three-dimensional picture?
Yeah, so I guess it's saying that somehow so we have this entanglement wedge that connects the black hole interior and the radiation system. And it's saying that if I look at the the domain of dependence of that entanglement wedge, right, which is something like this, and its domain of dependence over here, then the past of this is just causally connected to the future of this.
Right, and since this causal connection is purely in the three-dimensional picture, it would be some sort of strange phenomenon in the two-dimensional picture. But it's just
that's right, yeah.
Normal causality in the 3D picture.
It wouldn't be obvious in the two-dimensional picture.
Thank you.
Okay, good. So I think this is sort of just, I think, kind of re-saying things we've just been saying in another way, but I'll say it anyhow. So, one way you can think about this is, how do I have my radiation system? Apparently that encodes the black hole interior, but in some obscure way, right? This kind of causal perspective seems to give some insight into how I could write an operator that acts on that radiation system that tells me something about the black hole. And the way I would do that, right, is I would take my radiation system, think of that as the past of this, or the lower part of this diamond of the radiation system. And then if I use the global Hamiltonian, right, I can evolve the state on this orange region forward in time. And the theorem tells me that if I do that long enough, I'll get to a point, call it y, where a local operator acting on y is in the future of the black hole. So this operator just sees the interior of the black hole. Maybe if some particles scattered in here and released a photon, you would detect that photon. And so the suggestion is that a way to write an operator that sees the interior of the black hole would be to take this local operator and do some global time evolution. My pen seems to be decreasing in effectiveness, but okay.
Sorry, Alex, the fact that you can reach outside, isn't this saying that from the 3D point of view, it's not really a black hole?
That's what I've been asking. I'm wondering, what's your definition of a black hole? This has got me very confused. Is there a trapped surface here in the 3D? I'm a 3D relativist. Is there a trapped surface when you say there's a black hole? This is, this is what I've been puzzling about for a long time. Yeah.
Okay, I see. So, right. Yeah, I guess all I really precisely mean when I say black hole is there's the presence of these two horizons, and those two horizons are there.
Okay.
From the perspective of like restricting your attention to the brain, and restricting to a Poincare patch, right?
So it's sort of like a observer dependent horizon in that you can use a bigger patch, but if you restrict yourself to this, then you have a horizon.
Yes.
Okay.
Like the space, yeah.
Okay.
And continue the space time.
Okay, go ahead. Yeah, sorry, Shiraz, please go ahead. Yes.
Sorry.
Yeah, no, but just from the point of view of I'm willing to, you cut off your geometry the way you want, you put your end of the world brane. Yeah. But since signals can propagate from your end of the world brane to arbitrary points on scribe plus, to points on scribe plus of your Poincare patch, in the full 3D point of view, since from full 3D point of view, this is not really a black hole.
Sorry, so maybe just repeat what you said. I got a bit lost. So you said,
yeah, maybe I said it. You say
even with the
future of the Poincare patch. That's why.
Sorry, Shiraz. Even with the end of the world brane, there isn't, if I understand, there isn't genuinely a trapped surface and some null ray beyond which you can't reach out to the boundary. Isn't that right, Alex? But of course, if you choose a particular set of observers on the boundary, then they have a horizon. Is that correct, Alex?
I think so, yeah. So if you look at, if you restrict yourself to the Poincare patch, then this looks like a black hole. You have these two horizons separating the sides. But yeah, in the global geometry, you can perfectly well travel from one side to the other. So
yeah, and the way you described it, in fact, was it's really just AdS space, AdS3 in global coordinates going up to some rho naught. Let's say, when you wrote it as cosine hyperbolic square rho dx2 square, that gets cut off at some rho naught instead of going all the way. Isn't that right, if I understood?
Yeah, that's right. So this spacetime,
yeah,
it's just this metric.
Right. So then signals can definitely get out from everywhere in the bulk out to the boundary. But as you say, you choose a Poincare horizon. Okay, yeah. Go ahead. Yes. Sorry, should ask. Yes.
Yeah. No. Okay, thank you. But if you cut off your boundary the way you do,
yes,
then and you define scri plus of the boundary,
yes,
then signals cannot reach scri plus of the boundary from inside the black hole. Is this right? Even through the
that's right. You can't get from the black hole to here or something.
Yes, you can't. Right?
But you're getting from here out to somewhere outside the patch.
Yeah.
And then I'm just saying that I could use the global Hamiltonian and think about the state on, like, I can wind things back to scri plus and think about the state on there and think about that as the radiation system.
Right. But if you didn't do that, if you just cut off your space at the Poincare horizon, you cut off your field theory at the Poincare horizon, then this would be a genuine black hole geometry.
That's right.
Okay, thank you.
Yeah,
okay.
I have a question. Yeah.
Yes.
Yeah. So but the radiation region is not in the Poincare patch.
The radiation region is touching the Poincare patch. So let me erase all my scribbles here. So the radiation system is this black thing, and it rests right against the patch, and so I could, the state of the quantum fields in this black diamond are encoded into some portion of like scri plus.
Okay. Yeah. Okay. Thanks.
So if I'm calculating entropies and looking at entanglement wedges, I can look at this orange thing as well as I can look at the green thing.
Yeah. Okay, I understand.
Yeah. Okay. Okay. So I think that's about an hour. So I'm not finished, but I guess I can go over a little bit, or.
Yeah, go ahead, Alex.
Go ahead. Okay. So I'll try not to be too long, but I want to tell you about why this theorem is true. Okay. So the theorem, it's pretty easy to argue for it, but there's a little bit of a story to get there. And I need to sort of introduce a topic in quantum information theory. They're basically just quantum computations, except they happen in space-time. Okay. To talk about them, it's helpful to talk about Alice and Bob, like information theorists like to do. So in the course of this task, Alice is going to be someone who receives inputs, applies some computation to them, processes them in some way, and then produces the necessary outputs. Okay. And then there'll be Bob, who gives Alice her inputs and then verifies that she's produced outputs correctly. Okay, so this is just a quantum computation, except the catch is that the inputs and outputs occur at designated space-time locations. Okay, so Alice has to produce the output, but she has to get it to the right place at the right time. Okay, so a very simple example would be something like this. I'm just thinking in 1+1 dimensional Minkowski space. I have a point C1 where Bob is going to give Alice a quantum system A, and then Alice's task, or the thing she has to do, is bring A up to R1 and give it back to Bob. Okay. Good. So given a task like this, or maybe a more complicated one, maybe the most basic thing we can ask is, with what can we do it, and with what probability? So given a task, there's like a number we can compute with that's the success probability that'd be optimized over or maximized over all the strategies Alice could follow. And one thing about that is that it depends not just on what we give Alice and what she's supposed to output, but also on the location in space-time of where those inputs and outputs happen, right? So if I have R1 here in the future of C1, then it's easy for Alice to complete the task. And on the other, because she can just take A from C1 to R1 along some causal curve. But on the other hand, if I put R1 down here, then the success probability would be very low, right? If I put it outside of the light cone. Okay. Another sort of more refined question that we can ask about this task is, what resources are necessary to achieve a given success probability? So we could make statements like, let's assume Alice can complete the task with some minimal probability. What does that imply? And in particular, what does it? Yes.
Sorry. So why do you say very low when it's spacelike separated and not 0?
Oh yeah, that's a good question. So say I gave you a d-dimensional quantum system here, right? Alice could output the maximally mixed state on to R1, and then Bob will try and check if this state is the one he gave Alice, right? Mm-hmm. And there's some overlap between the actual state psi and the maximally mixed state, which will be like 1 over d. And so like with probability 1 over d, Bob will just like happen to get the right measurement outcome.
Oh, okay. I see.
Yeah. And so, yeah, so as d goes to infinity, then this would be 0.
Okay. Thank you.
Yeah, but yeah, it's a good question. I defended my thesis recently, and I got the same question from my committee. Okay, yes. So we can say, let's suppose Alice can do the task with some probability. That might imply something about Alice, right? So it might imply that she, say has entanglement distributed in the right way that helps her complete the task, or that she, has access to some classical information that helps her complete the task. Okay. So what does this imply? Okay. We'll see a more concrete example of that in a second. Okay, so here's the basic procedure to follow that's going to let us use insights from thinking about these sort of tasks and results that information theorists have proved to learn things about AdS CFT. So what we're going to do is pick a task, let's call it T, and we're going to define it in the bulk. Okay, so it's going to be like something that happens in the bulk with some input points and output points that are bulk points. And then we're going to identify some corresponding task, call it T hat in the boundary. And I'll on the next slide describe how we make that identification. Okay. And then we say, since the boundary describes the bulk, the success probability in the bulk should lower bound the success probability in the boundary, right? Because any procedure I could follow in the bulk to complete the task, I could map to some procedure in the boundary that will complete the task with the same probability. Okay. It's an inequality because I'm interested not in the full string theory glory of the AdS CFT duality, but in semi-classical bulk, in a semi-classical bulk description. So I've restricted my bulk picture, and that ends up giving me an inequality because, for instance, there'd be some processes that happen in the CFT that might complete my task for me, but that aren't described geometrically in the bulk, or semi-classically in the bulk. Okay. Right, so the way we're going to think about this is this success probability for t hat being larger than something. This is some kind of obscure looking constraint on the CFT. Okay, it's not the kind of constraint we usually care about for a CFT, so we're going to try and turn it into something we might care more about. For instance, this might be statements about entanglement wedges or statements about entanglement in the boundary between subregions or something like that. Okay. To make this procedure work, I need to tell you how to identify the boundary task, starting with the bulk one. What you should do is pick a bulk task with input and output points off at infinity, and then identify those points naturally with points in the conformal boundary, right? So just unrolling the boundary here, and I have my C1 and R1. And then there'll be some inputs, like some quantum systems that are input, say at C1, and some quantum systems that are output at B, or at R1. And I just identify those across the bulk and boundary as well. So, in the bulk and boundary, those would be in very different degrees of freedom, but at the level of quantum information, it makes sense to talk about the same qubit being recorded into those very different degrees of freedom. Okay. A comment is that you can also think about tasks where the points are pulled off of the boundary. It becomes a little bit more confusing how to identify the corresponding task. I discussed this in a recent paper. I'm not going to talk about it because in our setting, it doesn't help at all. But in some settings, you actually get a stronger theorem by doing that. Like this theorem I described earlier only goes in one direction. So there's sort of room for improvement in it. You can improve it somewhat by pulling your points off the boundary like this, though it's still not both ways. Okay, so that's the crank we're going to turn. And then just a reminder, this is the theorem we want to get to. So I think we've discussed this a lot at this point, so I'll just flash the picture to refresh your memory. And then,
yeah, I have a question about this t hat.
Yes.
So is the t hat unique for a given t? I mean, even in the case of when the points is taken inside the bulk.
So in the case where the points are pulled off of the boundary, yeah, it is still unique in the boundary. There's sort of, yeah, I mean, what you kind of have to do is say, okay, I'm going to have a qubit stored at this point in C1 or some quantum state here. And then that means it's recorded into the boundary in a certain way that's specified by, the AdS CFT dictionary. So it's in the entanglement wedge of various boundary regions.
Alex,
yeah.
Well, if the previous person is done, can I ask the next question?
Yes. Yeah.
Alex, something that's I'm not sure about, maybe I should wait till you discuss it more, is to the extent that the bulk light cone might decide how easy or hard something is. It may also depend on what you're prepared to do in the bulk, right? Because, I mean, if you're only willing to act with supergravity modes, they would preserve an approximate notion of the light cone. But if you're willing to act with very heavy operators, string modes, or even more, then they would do more violence to the light cone. So is part of, when you try and decide the probability, some notion of how you're going to be doing your various operations to make it defined, especially from the boundary theory point of view, some set of single trace operators or whatever, just to ask you.
Yeah, so, okay, so yeah, one place that this comes up is you have to think about if you say if you try and do a task which involves moving, say, more than order 1/g Newton qubits around, then you can worry that this is going to change your geometry and change your light cones. And so you're not going to be probing the geometry that you're interested in. And so what you do is work in a setting where, like, you think about tasks that involve n qubits, where n is less than order 1/g Newton. And in this way, the task just probes the existing geometry and doesn't change it.
Okay.
Yeah.
Thank you.
Okay. But yeah, working in that setting, you can still reach interesting conclusions. Okay. So okay, the way that we're going to argue for the theorem is using one such task. The task we're going to use is called the monogamy task. Here it is. So there's one input point, two outputs. Okay. At the input, we have a qubit. The qubit is described by this expression, HQB, where Q and B are bits, 0 or 1. H is the Hadamard operator. So H takes the 0 state to plus and the 1 state to minus, right? So that just means that if Q is 0, this is either 0 or 1. And if Q is 1, this is either plus or minus. Okay, so that's your inputs. And then what you need to output at the end, or what Alice needs to output at the end, is the bit B twice at R1 and R2. Okay. Okay. And then the way we get to the theorem is we think about this task in the bulk, as I was saying. And so here's the 3 points, C1, R1, R2. We're going to arrange them as occurs in the theorem that we're trying to prove, right? So C1 is in the AdS boundary, R1 and R2 are on the edge. And following the conditions of the theorem, we're going to pick them such that this scattering region is not empty. Or this brane-anchored scattering region is not empty. Okay. And then further, I'm going to say that this bit Q is going to be stored in the brane degrees of freedom. Okay. So it's classical. I'm going to copy it. I'll just think of it as stored like anywhere you travel to the brane, you can make some measurement and learn Q. Okay. So then we think about how can we complete this task in the bulk, right? In the bulk perspective. And it's very easy to complete there. So you take HQB, you bring it to the brane, right? You learn Q. That lets you undo HQ, right? So H squared is 1, or identity. So you apply HQ again and you get just the bit or the qubit B. You measure, find out B, and send it to R1 and R2. Okay. So this works. You complete the task with probability 1. Okay. So that's the bulk picture. Now the boundary picture. You think about the same task, but in the boundary, we have the setup causally looks like this, right? So there's this region V that we're interested in. That's the future of C1 and past of R1 and R2. And then what I'll tell you is that in this setting, if Alice can complete the task with probability 1, then it actually implies that the classical bit Q was stored inside the region V. So there's some way to learn Q from inside of V. And that's just because for Alice to get B sent out in both directions, she needs to undo HQ while she's inside of V, and she needs to know Q to do that.
Okay. Sorry, this entire diagram on the left is on the boundary, right? The light cones are all boundary, etc. Right? Yeah.
Yeah, that's right.
Mm-hmm.
Yeah. Okay. Yeah. So I've specified where Q is in the bulk, but I haven't specified where it is in the boundary.
Yeah.
But I'm saying in order for the task to be completed in the boundary, it must be inside of V.
Hmm.
Okay, so then we just put the two perspectives together and that'll get us the theorem. So we say, first of all, in the bulk, the success probability was 1. That was because the scattering region wasn't empty and there was an obvious way to do the task. And then we said, in general, there's this inequality here between the bulk and boundary success probabilities. And so then we learn that the boundary success probability is 1. Right. Then, as I was arguing on the last slide, if the boundary success probability is 1, that implies that Q is inside the region V. And, we know from our understanding of entanglement wedge reconstruction that for V, this region down here, to learn Q, which is sitting on the brane, it must have its entanglement wedge include a portion of the brane, right? And that brings you to the theorem. Is there any questions about that?
So you're basically using the causality, the fact that you can scatter, therefore, in the bulk and be causally connected in the bulk to say that you should be able to carry out these operations.
And then in order to be able to carry out these operations in the CFT, V needs to know.
Could you just explain that a little more, as in, suppose in the boundary theory, I thought the interesting case is that it seemed on the boundary that the points would not be causally connected, but they are causally connected in the bulk.
So,
when you first put it like that, right? Isn't that right?
So it's a bit subtle. So in the bulk, this intersection of light cones on the brane, restricted to the brane, is not empty in the bulk.
Mm-hmm.
And then that same thing, but in the boundary, that's V intersected with the brane, and that is empty. So I intersect the light cones, I get this thing, but it's not touching the brane, which would, in the boundary, is just this edge. And so because of that, it's not immediately clear that V knows Q, right? Because Q is stored in the brane, so also in the edge. But V is disjoint from the edge. But the theorem ends up concluding that actually V must know Q, and it does that by having its entanglement wedge reach the brane through the bulk.
I see.
Okay. Yeah, so I think, maybe one comment about this is I'll just give a warning that I'm packing a lot of technical work into this statement. It's not as obvious to prove as you would think, but leaning on some other people's work in quantum information theory, you can find the techniques to make this precise. And yeah, so that's one thing to note. I think that this gives you some intuition as to why this theorem is true. It would be nice to connect this more closely with the sort of black hole picture that I was talking about before. It's slightly awkward in that my intuition gets all confused because I didn't quite use this theorem. I used its time reversal. And so if you want to kind of think of this task happening in the black hole context, you have to think about your particles moving backwards in time. And I don't know, I'm not quite sure what to make of it, but anyhow, this is where the theorem comes from. Okay, so that's everything I had to say. just a couple remarks to conclude. So this quantum tasks idea, it captures more relativistic aspects of quantum information, right? We think about quantum computations, but we think of them really happening in a space-time context, and how the causal features of the space-time and the arrangement of points affects the quantum information processing task. And in doing so, we get this connected wedge theorem, which relates causal features of the bulk geometry to entanglement in the boundary. Okay. And then in the context of these brane models, or applying this to brane models of black holes, we found this interesting conclusion that when the black hole interior was connected to the radiation system through the higher dimensional AdS, then the radiation system had an island, which was, yeah, okay. So that's everything. Thank you. And thank you for your many questions. It's good. And I'll take further questions.
Thank you very much, Alex, for a wonderful talk. Let's all please unmute ourselves and thank Alex. More questions?
Yeah, well, maybe I should wait, but
well, could I ask a question then? In the Sandeep, do you want to go ahead?
No, go ahead, Omkar, please.
Okay. I actually have a couple of questions. So the first, maybe a more simple-minded question is there like a way to probe these or set up, I guess, quantum tasks in quantum field theory, like in terms of correlation functions or something like that? Is there a way to do that?
Yeah. Yeah, I haven't thought that hard about it. I think partly I haven't been as motivated to think about it hard as I maybe otherwise would be, in that both the theorems I described today, like the one with 4 points and the one with 3, you can just prove using the focusing theorem and general relativity. And so this makes me a little bit happy with kind of like a slightly heuristic quantum information argument, lets me find the statement of the theorem, and then I go prove the statement of the theorem using some other technique. But I think it'd be very interesting to do. And I think one sort of interesting comment there is that, you know, these kind of setups where you're interested in scattering that, like a point in the bulk that's causally separated, or a non-empty bulk scattering region and an empty boundary scattering region. This sort of correlation function was studied, well, it's been studied in a number of contexts, maybe most famously by like Jamie Sully and Polchinski and others, when they were thinking about like, what are the conditions on a CFT to be holographic. They found that these 4-point functions have this interesting sort of perturbative singularity when all these rays are light-like. And, you know, exactly when all those rays are light-like and you get this singularity is exactly when this theorem tells you that you get a connected entanglement wedge. And so it'd be really interesting to connect the like correlation function perspective here with the entanglement perspective. And yeah, I don't know if I have any comment, like, yeah, I haven't made any progress on this problem. I've talked to Jamie about it a bit, but he also didn't seem to have any clear ideas forward. So, but yeah, I think it's a really interesting direction.
And maybe if I could ask just one quick other question, the statement about, you know, there being this auxiliary causal relation that comes out of your theorem in this island case. You know, for example, even without the 3D bulk geometry, like there is the Spets reconstruction that one could do, right? Like
yeah, right.
But in that case, like, you know, for example, this paper by Kim, Preskill, and Tang, they sort of make a statement that, you know, these operators must be sort of exponentially complex, or they must be somehow complex operators. So that they don't just violate like semi-classical causality. But somehow you're saying that, so I mean, maybe this is a vague question, but somehow there's a statement where if you just try to restrict to 2D, then the reconstruction is complex. But if you allow yourself this 3D geometry, then it becomes simple somehow. Is there some restricted complexity kind of?
Yeah, I think it's a bit different though, in that like so this kind of picture lets you write like an operator, like I was talking about operators like that are local, and then you have some time evolution with the global Hamiltonian. And these are like operators on the radiation system, but those aren't operators that actually live on the black hole. They're just in the future of the black hole. So they sort of see the interior in a causal sense, but they don't actually live in the interior. This procedure doesn't give you any way to write down a simple operator that actually is in the interior of the black hole.
Oh, I see. Okay.
And so I don't think it's in direct tension with that kind of statement.
Okay.
Yeah. But
I see. Okay. Okay, great. Thank you so much.
Sorry, can I ask you a question, Alex?
Yeah.
And it's actually even about your talk, but even more generally, let's take the theorem you mentioned, even without end of the world branes.
Yeah.
And so this is really saying I don't understand that theorem. But, when I learned the EPR paradox, it was emphasized that entanglement doesn't mean you can send a causal signal, right? The light cone is absolute, say without gravity, for example. Now I'm just trying to understand what you're telling me. Let's take the case, just to make it all very simple, no end of the world brane, if you don't mind, just the case where you have AdS in the bulk. Now, aren't you telling me that you can have a situation where you're allowed to have scattering in the bulk? Causally, the 4 points, the 2 in the future and 2 in the past, cannot be in touch with each other if you were just on the boundary. But because, was that correct or was that wrong?
No, so it's still true that C1 is in the past of R1 and R2.
Yes, that's true. But could I have sitting on the, I thought you said the interesting case is sitting on the boundary, I could not have sent signals from C1 and C2 to meet up somewhere and reach R1 and R2. Or,
that's right, yeah. So there's it's this that doesn't happen, right?
It's this that doesn't happen, right? But maybe the point is that, what I'm trying to ask is just, all right, so now there's mutual information or something in the boundary, across regions, fine.
Yep.
But that shouldn't allow me to send causal signals outside the light cone in the boundary itself. And presumably that doesn't happen.
No, that doesn't happen. That's right. Yeah.
So okay, yeah, go ahead. So just this part, if you don't mind. So the bulk, yeah, please go ahead. Go ahead.
So yeah, it just says, okay, V1 and V2. Okay, I think, so I didn't talk about the quantum information story for the four-point theorem, or the 2 to 2 theorem, as I like to call it. But the sort of picture you should have in mind is just a schematic picture. So I'm just kind of drawing things in flat space. But, so the bulk picture looks like this, right? You can meet in the middle.
Yeah.
So yeah, the causal features of the relevant points as they fit into the geometry are captured by this schematic diagram.
Mm-hmm.
In the boundary, you instead have the following. So okay, so now you can't meet in the middle, right? But you can send signals from C1 up to R1 and from C1 over to R2.
Okay.
And so on.
Okay.
And basically, the way the quantum information argument for this theorem works is it says anything like any of these tasks that you can do using this kind of a causal structure, you can do here, but only if you have entanglement between these starting points.
I see, I see. So there's some analog of a teleportation type of thing, that is involved, without which you would not be able to achieve this task.
That's right. Yeah, that's right. So it's like in terms of doing tasks, like doing stuff, you can have two sets of resources that let you do the same thing. You can have a strong causal structure where you could meet in the middle.
Yeah.
Or you can have a weaker causal structure where you can't meet in the middle. You can still send signals between people, but you can't meet in the middle. But you make up the difference with entanglement.
Okay, now this is very interesting. I see. So that's what's going on.
Mm-hmm. In this theorem, that's what's happening. Yeah.
I see. Okay, now I begin to understand. I see. Okay, thank you very much. And it's a go ahead, please.
All right, this is described in detail in a slightly earlier paper of mine with Jeff Pennington and John Source, and it has the GR proof of this as well, which is nice.
I see. Okay. Thank you very much. Thanks.
Sorry, can I ask a follow-up question on this one? So you said that C1 and C2 should have some entanglement. So how much entanglement is it? Like, is there some minimum amount of entanglement for which this should happen?
So that's a good question, and comes back to something that was asked earlier as well, which is basically in the bulk picture, you think about a similar task to the one I described. So I described this monogamy task. Here you think about almost the same thing. So you think about putting a bit Q in here and then putting this quantum thing, this quantum qubit in at C1. And then what you can show is that to do this task, so, in the bulk picture, you meet up in the middle, you undo HQ, you find out B, you send it out. To do that task here, you need one EPR pair.
Yeah, it seems like that. That's what I would have thought. You're able to do a flip you couldn't do otherwise.
I see.
So then what you do is you think about repeating this task in the bulk n times in parallel. So they all happen at once. You pick a bunch of independent Qs and a bunch of independent Bs. And then you learn that you need n EPR pairs over here. Okay. So then you ask, okay, well, how big is n in terms of, what I'm interested in? And the argument is like, well, in the bulk, if I keep n any order less than order 1 over g Newton, right? It could be like 1 over g Newton to some power close to 1.
Right.
Then I'm not going to back react, and I'm allowed to do that. Right? It's not going to change my geometry. And so I should have basically 1 over g Newton EPR pairs. And that leads to the statement that the mutual information should be order 1 over g Newton.
I see. Okay, thank you.
Well, you could probably do it with less than 1 over g if you just had 2 qubits that you were going to do, but you want to be able to do it for even coherent state scattering there or something,
I want to like
to get.
I can pick n.
Yeah, go ahead.
I get to pick n to be whatever I want, little n to be whatever I want.
Yeah, and still
I want to.
Yes.
I want to pick it as big as I'm allowed to like lower bound how much entanglement there must be in the in the CFT, and so I take it marginally less than 1 over g Newton, and
I agree. That's the upper limit, and therefore the mutual entanglement information had better be as big as this.
Yes.
I agree. Okay, very nice, beautiful.
Sorry, and at some point you said that the converse of this theorem does not hold. Is the eternal black hole an example of a situation where you have a connected entanglement kind of thing, and yet you can't meet in the bulk.
That's an example. Yeah. Another example, the one we talk about in this paper, is just like a dust ball. So if you can construct an example just with some ordinary matter spherically symmetrically distributed in the middle of AdS, and if you carefully pick your regions so that they like I've divided the boundary into quarters evenly, then you can get a counterexample here. So you note that the dust ball will make your light rays go slower, and then okay, yeah. So you pick a case where V1 and V2 are a quarter of the boundary. That puts you without the dust ball, or even with the dust ball, I guess. It puts you right on the transition between connected and disconnected, just by symmetry. And then you notice that the light rays will go slower with the dust ball, and then you shift these slightly to get the connected wedge. And so in this way, you can construct an example where your light cones don't overlap, but you have a connected wedge.
See. Okay, could I ask one more probably stupid question? Suppose you had one of these eternal black holes that were pulled in by this mechanism that these people talk about, right? I can't remember who. Jefferies wall.
Oh, like a traversable.
Yeah,
wormhole.
traversable wormhole.
With the with coupling.
Is this a situation where you can scatter in the bulk or not?
Yeah, so if you, okay, so they have their horizons. They have these shock waves that come in from turning on the coupling. And that makes it so light rays go like this and come out the other end. And so, yeah, you could scatter in the bulk.
Right.
And you would conclude from the theorem that the mutual information should be at least as big as the number of qubits you can send through the wormhole. But you didn't really learn anything because you started out in the thermal field double state, which already had
a lot of mutual information. Yeah, I was wondering though that this causal situation on the boundary is a bit different from what you had described, because on the boundary, both points in the future are not to the future of any one point in the past. Right, the guy on the left is the future of the guy on the left, and the guy on the right is to the future of the guy on the right. But on the boundary, they're disconnected boundaries.
Well, so, once you put the coupling in, though.
Ah, yes, thank you.
That's not really true.
Yeah, okay, thank you.
It's not geometric, so it's a little bit confusing to think about. But you should probably think of C2 as in the future of. Well, yeah, I mean, through the bulk there, it's in the future, so it had better. However you think about it.
Thank you. Yes.
If I can just come back to the previous comment of Shiraz's and what you were saying, namely the converse not being true, Alex, what is the quantum information understanding of that? As in, you can have a lot of mutual information, but even so, I mean, this is not a matter of not being clever enough, right? Because in the bulk, you just didn't have scattering possible, at least with supergravity modes and so on. So even though you got order 1/g Newton mutual entanglement, no attempts at teleportation and so on are going to allow you to connect the past with future. So what is there a sort of understanding? Of course, I should read it in some paper, but just briefly.
Yeah, I mean, so I think there's various possibilities. There's various possibilities on the QI side why you could have large mutual information but not be able to do this task. So one would be you have large mutual information, but it's all classical correlation. So you just have like a shared random string.
I see, but doesn't the Ryu-Takayanagi, I see, you mean we don't know whether the Ryu-Takayanagi computes the number of distillable bell pairs for sure, is it? It doesn't because it's in the gauge theory, but all right, okay, maybe I can ask you off. I mean, I thought the Ryu-Takayanagi mostly computed distillable entanglement. Or
yeah, I think that's a fair statement. So yes, this is naively, this is one possibility.
Okay.
If you argued like about, if you used our maybe more detailed understanding of what kind of states, what kind of entanglement there is in these geometric states, and said, no, it really measures in this case entangled particles. Then it's a little bit more confusing, but okay, one possibility is that, and I would suspect that this is the correct possibility. So one statement would be, there's large mutual information between the regions, but in order to access it, you have to do some kind of like high energy operation, which
the supergravity
wrecks your bulk picture. So some kind of operation in the boundary would let you get that entanglement, but that doesn't correspond to any kind of semi-classical description in the bulk, and so we shouldn't expect there to be like an overlap of light cones.
Not the light supergravity modes, your order n less than 1/g Newton can't get it out.
Yeah, that's right.
Okay, interesting.
Yeah, so if I had to guess what a theorem like this with a converse would be, it would be some kind of like, there should be some kind of other measure of entanglement. Let's call it I-twiddle, that sort of like counts the number of EPR pairs accessible to somehow a low energy observer. I don't know how you would define that precisely, but heuristically that feels like what would give you a two-way theorem.
Okay, got you. Thank you very much.
Do we have any more questions? Okay, if not, let's thank Alex again for a wonderful talk.
Thank you. Thanks a lot, Alex.
Yeah, thanks everyone. Thanks for the questions. Very engaging talk, or engaging audience.
Thank you very much, Alex. Thank you for staying up. It's probably quite late for you, right?
Oh, it's okay. My schedule has not been as regular as it should be with COVID and things. So it's only 10:30 here. It's really not quite that late.
Okay. See you.
Bye.
Okay. Bye. Yeah. Bye. Thanks.